Current methods of reentry from the International Space Station are gated by incredibly long wait times, bottlenecking the type and number of possible projects. An external investment company reached out to us to create a reentry vehicle capable of returning a 1 kilogram payload from the ISS to Earth in a pre-selected landing area. The overall system is designed for affordability and would greatly reduce wait times for the low Earth orbit reentry.
The beginning of the reentry mission starts with the astronauts on board the ISS installing the payload into the Aero vehicle and loading it into the NanoRex CubeSat deployer. The external interface constrained the team to a maximum size of 6U linear CubeSat with a maximum mass of 8.4 kilograms. The orbital mechanics subteam calculated and simulated the orbit burn by utilizing the time dynamic position and attitude determination computer software SDK. After being launched from the NanoRex CubeSat deployer with an impulsive retrograde delta V of 2 meters per second, the reentry vehicle will exit the ISS keep out sphere and then complete a finite retrograde burn to achieve a delta V of 90 meters per second.
To achieve the required delta V, the team decided to use an off-the-shelf onboard propulsion unit. After some trade studies looking at the size, mass, and efficiency of propulsion units, the team chose the PM200 bipropellant propulsion module. It has a compact 1U configuration and a low mass of 1.41 kilograms. Most importantly, the PM200 gives the vehicle the required 90 meters per second delta V, and is capable of performing thrust vectoring for small attitude corrections.
Once the deorbit burn is completed, the heat shield system deploys to decelerate the vehicle through the atmosphere and protect the payload and rest of the vehicle's systems from excessive heating. The heat shield system doors were designed with simplicity and reliability in mind, so they are spring-loaded and interlocked with each other so that one actuator locks and unlocks them. Once the doors open, the fabric tension cone heat shield is expanded by inflating its doors using a small CO2 tank and an electronic valve. For the sizing and material determination of the heat shield and other key systems such as the parachute, insulation, and structure, the team created a standard atmosphere ballistic reentry simulation to analyze the vehicle's aerodynamic characteristics, loads, heating, and mission profile.
Following the mass, volume, and safety requirements imposed by the ISS and its NanoRex CubeSat deployer, and using the re-entry simulations, the size, shape, and materials of the vehicle systems were selected to minimize ballistic coefficient. Then, modified Newtonian flow and computational fluid dynamic analyses were performed to get the vehicle's stability range and confirm results obtained from the approximate methods. From this, the heat shield was designed to have a 66 centimeter or 26-inch diameter with a half-cone angle of 76 degrees, yielding a drag coefficient of 1.6 and a ballistic coefficient of 13 kilograms per meter squared for a vehicle with dry mass of 7.1 kilograms. The estimated total flight time from deployment from the ISS to touchdown is 1 hour and 50 minutes, with a peak deceleration of 8.5 Gs and a maximum nose stagnation temperature of 1,750 degrees Celsius.
Given that the expected peak stagnation temperature is very high, in order to avoid thermal failure of the heat shield and keep the payload and bus from overheating, the team designed the main thermal protection system in two parts: an ablative cork phenolic nose cone to protect the stagnation region of the vehicle, and a tension cone heat shield made of Nextel heat-resistant ceramic fabric. This heat shield system configuration provides adequate heat protection, keeping the vehicle's average internal temperature at 27.6 degrees Celsius during atmospheric reentry.
The lightweight aluminum 6061 structure is designed to survive an expected peak acceleration of 8.5 Gs while optimizing the vehicle's internal volume. Design was limited to a 60 by 10 by 10 centimeter box for the volume and a vehicle wet mass of 7.4 kilograms, which had to be partitioned effectively between subsystems. The structure bus was also designed to be simple to manufacture and have easy access to all subsystems.
Following the completion of the supersonic re-entry process, the vehicle deploys a subsonic parachute and touches down. Ground crews locate the vehicle and retrieve the payload, thereby completing the mission. At a top level, our vehicle consists of a commercially off-the-shelf or COTS propulsion module, a COTS attitude determination suite, a subsonic parachute, a 1U payload bay, a COTS reaction wheel array, and our custom thermal protection system.
As previously mentioned, the Aero reentry vehicle is a commercially viable product. By significantly reducing the expense and reentry time necessary to return payloads from the ISS, Aero alleviates a significant obstruction encountered by research that produces time-sensitive payloads. Unfortunately, due to the budget and time constraints of operating within a university setting, a full manufacture of the vehicle was infeasible. However, this creates the opportunity for future projects to further develop the reentry vehicle.